Physics. Hey. Okay. Um, we left off last talking about the lab a little bit. Please don't forget to do lab. I don't know that I was super clear. You do not actually need graphs for this first lab. The first lab that we're doing here is a like brute force calculation, doing multiple calculations, doing multiple more calculations, taking the average of those calculations. This is like the most blunt way to approach this, like taking a sledgehammer and just hoping that each hit is going to break it down. Um, as we kind of get more sophisticated into it, what I want you to focus a little more on is like actually writing the lab, getting used to the segments of the lab, what to include where. Um, don't need to worry about graphing yet. Graphing is something that's a little, again, it's a little more elegant. It's like, I don't need to bring this giant sledgehammer. I can take a little hammer and chisel and eat away at things that way. Um, but I'd like to focus on a couple of equations. A couple, really just one. There's only one new equation I'm going to mention today. The equations are related to these graphs, right? Which is why I'm kind of here in this section instead of over here. Also, like, this was the lab stuff. So, if I kind of continue on here, then what I'd like to focus on is, right, and I guess I don't need this graph to be that big. Oh goodness, why? There we go. This is distance measured in meters. This is time measured in seconds. And if I look at this, right, this is a relatively straight line. I tried to draw it as a relatively straight line. And the reason I drew it as a relatively straight line is because lines are typically in the form y equals mx plus b, right? And we talked about this graph, specifically the distance time graph, and how the velocity can be represented by the slope of the graph. So m is the slope of a graph, right? I'm going to write an equation that you should be relatively familiar with, which is that velocity is distance over time. This is one of the first equations, I think literally the first equation on the reference table. I'm just going to put a delta in front of it. I like to have that delta because it means change, right? Change in distance over time. How much distance are you covering over a specific amount of time? Just feel kind of washed out. All right, that's a little better. All right. I bring this up also because, remember from last year, delta something is the final minus initial. So I could rewrite this as velocity is the final distance minus the initial distance divided by time. And if I want to figure out what the final distance is, I can multiply both sides by time. And then I can solve for the final distance. So I could say that the final distance is equal to the velocity times the time plus the initial distance. And if you look now at a possible connection between these equations, you should see it. The final distance is our y value, right? The velocity is the literal slope. The x value is the time. And the initial distance is the y-intercept, right? Where does y equal 0? Or, sorry, where does x equals 0, right? If x equals 0, that's your y-intercept. So where did you start? Where did we begin? In this case, we're beginning at the origin, but if the line was drawn, I don't know, down here, then it would be a different y-intercept, but that would be reflected in this equation. All right? So I'm trying to make like connections here, right? That's my whole goal. Physics is about making connections. There is another graph that you should be, relatively familiar-ish with. It's the velocity time graph. And I could draw it again. Very similar. And if I did this, this represents a graph where the velocity is changing, which means that there's acceleration. I can do the same thing here. Change in velocity over time, which means that acceleration is the final velocity minus the initial velocity divided by time, which means that acceleration times time is vf minus vi, and it means that the final velocity is acceleration times time plus the initial velocity. And again, you should see a connection between these two, right? I'm pretty sure we said, that the acceleration is the slope of velocity time, right? Now, you can use this equation when there's no acceleration to find the distance. You can use this equation when there is acceleration to find the velocity. What we don't have is an equation to find the acceleration or the velocity or the distance, or really the distance. We don't have an equation for distance when there's acceleration. That would have been real helpful when we were doing the lab that y'all just tried to do, because again, brute force. It was a brute force lab. Calculations on calculations on calculations. There are more elegant ways. The more elegant ways typically involve making an analysis of some kind of graph that might look like this. This is again distance in meters, this is time in seconds, and this is the form of a parabola. And if maybe you remember, maybe you don't, but the form of a parabola is ax squared plus bx plus c. I'm going to scroll down here because I'm going to work on this. Now, if you look at your reference table, if you were to look at your reference table, and let me bring up a reference table here. I'm pretty sure that I have one. Let's just see how handy it is. Not very handy, but that's okay. What we're going to do is check the interwebs. Alright, so here we are. This is the reference table, and this is the equation that I was talking about. So we do, this was the first one, there's the second one, this third one, right? That third equation is the one that we just defined here. You should see that the third equation and the second equation are in fact the same equation, simply expanded, right? Now let's look at this equation. I call this equation the big one because it has the most variables. It tends to be the most confusing. This is the equation that you can use to find the distance an object travels as it's accelerating. Because distance and acceleration. Now, it's a little troublesome because it looks super complicated. The reason it looks funny is because if you remember, right, I talked about it up here, these are the distance graphs for an object with acceleration. And just like these graphs resembled the line, or sorry, these equations resembled the equation for a line, the equation for this should resemble the equation for a parabola. So, if you look, the way that it was listed there was d equals vit plus 1/2 at squared. I'm going to rearrange this just the tiniest bit. And I'd like you to do this if you haven't already. I think I had you do this in class, but I'm going to say it here too. This should be a delta d. Delta is final minus initial. So let's call this distance final minus distance initial equals vit plus 1/2 at squared. And I'm going to bring distance initial over because I'm not a big fan of using negative numbers if I can help it. I recognize that they're numbers, they're perfectly good. I simply, it's just easier to visualize positive ones. So our final distance equals, and I'm going to rearrange these guys a little bit, 1/2 a times t squared plus the initial velocity times t plus the initial distance. And now look. Now let's look at this form, right? I have a t squared, a t, and a no variable form. Well, that's x squared, x, and c, because t is my x variable. My final distance, right, is the y, right? So where did I end up? This a is representative of 1/2 the acceleration. This b is representative of the velocity. This c is representative of the initial position, the initial distance, where you started. Each of these terms, the reason that some of these equations look a bit funny, or might look a bit funny at first, is because they directly resemble some of the math that we're doing. Alright? Now, typically when you have to use this, it will simply be in this form, right? And you might see something like a car going 20 meters per second accelerates let's say 5 meters per second squared for 3 seconds. And I might say, how far does the car travel? How far does the car travel? Well, now that we have the equation, we can do the math. The change in distance for this car is equal to the initial velocity times the time plus 1/2 of the acceleration times the time squared. Now please be careful, please, seriously. Do not lose this half and do not lose this squared. I've seen many a physics student very confused as to why their answer doesn't match up with any of the multiple choice answers, or not understanding, why did I get this wrong? Look, I have all the work here, and I punched it into my calculator, and I didn't get the same answer that you did. I don't understand why. Please check your half, please check your squared. When I do this, I should get 60 meters plus 2.5 meters per second squared times 9 seconds squared. And when I do 2.5 times 9, I get 18, 22.5. So I should get 60 meters plus 22.5 meters, which is 82.5 meters. This is how far you've gone. This, for the record, is, I think, between 50 and 50, 20 meters per second is like 50 miles an hour. So this is you passing someone. If it takes you 3 seconds to pass someone, then you've gone almost an entire football field in order to pass that person, going from like 50 to 60-ish. Guys, that's a long way, right? If you're going to pass someone, use caution. I know that seems strange. If you're going to go fast, use caution, but seriously, use caution, okay? Now, another way, right? Another way that the question might be asked is, a person drops a ball from the roof of a 10-meter tall building. How long till the ball hits the ground? Now here, in this question, it doesn't appear as though you have enough information. Because again, if we look at our reference table and we look at the equation, my change in distance is 10 meters, right? That's the first piece of information that I got. And then I just asked me for time, right? So it looks like I have this. I'm looking for time, but it looks like I don't have an initial velocity. It looks like I don't have an acceleration. Oh gosh. So how am I supposed to do this question, right? If I were to list out things, and this is something that I would recommend. I didn't do it in the first question because I was just kind of doing the example, but when you see a word problem, I would recommend, like, change in distance is 10 meters. Time is unknown, right? List out the things that you have, because often that can kind of steer you towards, oh, I have this information. That's enough to use this equation. Let me try it, right? This is where I get to tell you about another part of your reference table. And that other part is actually the very first page. It's a list of constants. One of the constants is here. It's lowercase g, and it's the acceleration due to gravity. This number is how much gravity is pulling you down at all moments towards the center of the Earth. It's pulling you down, right? So it's 9.8 meters per second squared down. Now, if I look at this, there's a key word here, right? And the key word that I need you to kind of keep track of is drops, right? If you see drops, drops implies two things. One, initial velocity is 0. Second thing that it implies acceleration is g. When you drop something, you are taking it, there we go, you are taking it and you are releasing. You are not throwing it downwards, you are not throwing it upwards, I'm not throwing it sideways, I am simply taking it and dropping it. Because that's all I'm doing, the initial velocity of the object is stopped, right? When I let go of this, it takes a moment. There's an infinitesimally small period of time that it begins to accelerate. And the reason it begins to accelerate is gravity. So, I do actually know that the initial velocity is 0 and that acceleration is 9.8 meters per second squared, and that's down, right? So, if I look, I use my big equation, right? And my change in distance is velocity times time plus 1/2 at squared. So I'm going to do this. Change in distance is 10 meters. That equals 0 times time plus 1/2 times 9.8 meters per second squared times time squared. Now this goes away because anything times 0 is 0. So 10 meters is 1/2 times 9.8 meters per second squared times t squared. Now, normally I would do this math, but this is about 10. 9.8 is almost 10. So t squared is, give or take, 2 seconds squared, right? That is not my answer. I need to take the square root of this. If I do that, then I get that time is about 1.4 seconds. Ish, give or take. Alright? Okay, we'll talk more about this. We'll do more examples of this, right? Your next in-class day. And then, after that, we'll get into projectile motion. We're starting to talk about free fall right here, but we'll get into like formal definitions soon, right? We'll do that on Wednesday or Thursday, depending on when you have class. In the meantime, please finish the lab. You'll upload that as an assignment to my CBA. And as always, let me know if you have any questions. Right? Take care, physics. See you soon.